about this train. Woo! Lots of parts to this train. All right, so I'm not going to read the question because there are lots of parts. So we're going to have to kind of move through this if I want to fit it into one video. All right, so we have the forces on the 3,000 kilogram car. We have FW. We have the normal force, the two easy ones, right? And then we have this T3. Then we have down, up, FN, FW2, right? If that's the second cart. And then we have T2 going this way. And we have T3 going this way. Which one is greater? The direction that we're moving, right? We're accelerating 2 meters per second squared to the right. Forces on the 1,000 kilogram car, FW, FN, T1, and T2, which should be equal in magnitude. So this needs to equal this. Opposite in directions. This is a Newton's third law, force pair, right? Same thing here. T3 here has to equal T3 there. Sorry if it doesn't. Drawing not to scale, but yours better be. All right, let's go ahead and do Newton's second law equation because we know that's what it's going to be. T3 for this one equals MA. This stuff that makes it go is T2 minus T3 equals mass times acceleration. And then this one, T1 minus T2 equals mass times acceleration. On the squares below, draw external force diagrams showing the only external forces acting on the systems indicated. Please omit forces that balance. For each diagram, write an equation that relates. You know, we've done this before, so we're not going to do it again. Forces, to identify this, well, I say we're not going to do it again, but then I just keep talking. Just give them a break, Scapetus. Jeez. All right, so this system here, 3,000, 2,000, T3 is internal and T2 would be pulling those. But the thing with this is it's going to cause a lot more time to be wasted. So in an effort to limit you, I'm just going to go ahead and put this on here, skip. And that's because I already have equations that are serviceable up here. So we can just go ahead and figure this out from here. All right, so using the equations you wrote from above, so we have T3 equals mass times acceleration. So that's mass of the third car times acceleration. The acceleration, remember, is 2. I think that was given to us. 2. The mass is 3,000. T3 equals 6,000 newtons. Okay. T2, we have T2 minus T3 equals MA. T2 is what we're solving for, so I'm going to add T3 to each side. So I have T2 equals mass. Running out of room here. Mass is 2,000 times 2 is 4,000. Please don't say, would you get 4,000? Rewind. Watch it again. 4,000 plus that 6,000 T3, because remember I added T3 to each side. T3 we said earlier 6,000, so I'm going to add it over here. T2, 10,000 newtons. 10,000. 10,000 newtons. T1. Same situation over here, so I'm going to say T1 is MA plus T2, and T2 is 10,000, and M is 1,000 times 2 is 2,000 plus that. So T1 equals, boy, I just got some deja vu. Maybe it's the amount of times that I've stopped this and had to restart it. 12,000 newtons. That's not true. All right, so 12,000 newtons. So there you go. We have T1, T2, T3. D is asking for us to, without reference to any math or numbers, explain why T1 is the greatest tension and T3 is the weakest tension, even though they're connected, even though T3 is connected to the greatest mass. All right, so what I'm going to say is what you should have written should you do this. T1 is greatest because if you look at this entire train here, this tension right here is not just pulling T1, or is not just pulling cart 1. It's pulling cart 1 plus cart 2 and cart 3. So of course the tension in the front of the train is going to be greater than the tension in the back of the train. Tension T3, yes, mass 3 is the largest, but that's the only thing it's having to deal with. That's it.